Okay, so any other difficulty in that part? Can anyone see that recording has started or no? Confirm that one.
Yes, sir, it
Yes, sir,
started.
it is
Okay,
started.
fine. Okay, let's move on to the problem then. If you don't find any difficulty as of now. Okay, right. So first what we'll do is we'll deal with the non-sway frame. Okay, a simple non-sway frame. So what you have here is you need to analyze this frame, what is shown here, and draw the Benevolent diagram and the deflected shape. And it is given to us that the EI, flexural rigidity, is constant. Okay, so this is the frame what I have here, two members. Okay, so the loading, member length are shown here. And what about the degree of static indeterminacy? Okay, so degree of static indeterminacy in this case, it is 3. 6 reactions totally minus 3 conditions of equilibrium. We come up with degree of static indeterminacy as 3. Okay, so first step, what you have in this, finding the fixed end moments. Okay, so for one of the member AB, it is quite simple as you do in your beams. So the fixed end moment directions, this is what you will come across, the fixed end moment directions. So one of the fixed end moment, MFAB, you have it as minus WL square by 12, and load intensity is 30 kilonewton per meter. So I substitute those values, and what you get is minus 90 kilonewton meter is the fixed end moment at joint A for member AB. Okay, MFAB, it is minus 90 kilonewton meter. Same, what happens for the end B of member AB, MFBA, it will be plus W square by 12. Okay, so that will be 30 into S6 square by 12, it will be 90 kilonewton meter. Okay, at end B, this is MFBA. Now for the column, okay, now what will be the directions? Okay, so either you can just consider that beam. Okay, you can just look it as a beam, as a horizontal member, and the direction of the fixed end moment will be opposing the movement that is developed due to the applied loads over here at this joint. Okay, so like you identify the direction for the beam, in the same way the direction for fixed end moment in case of columns have to be identified. Okay, so the thing that will decide is that will be opposite to the movement caused due to the applied load. Okay, or you can just rotate it, look it as a beam horizontal member, and draw the moments, fixed end moment directions. Okay, so at B, for member BC, at joint B, my fixed end moment will be in anti-clockwise direction, what is shown here. Okay, and at C, it will be in clockwise direction. Okay, so 90 kilometer meter, it is having an anti-clockwise movement about C. When I look at this, so my fixed end moment, it is a reactive movement or a reaction at C, so it will be opposing this moment. So it is in clockwise direction. At B, it is coming out to be anti-clockwise. So with this direction, I'll go with calculation of fixed end moment in member BC. Okay, so MFBC minus WL by 8. So that will be minus 33.75 kilonewton meter. And MFCB, okay, since this is applied at the center, it will be WL by 8 itself, but sign will be positive. So MFCB will be plus WL by 8. So how much it comes out is 33.75 kilonewton meter. So I have the 4 fixed end moments for these two members. Okay, MFAB, MFBA, MFBC, and MFCB. These are the values of fixed end moments, what have been written here. Okay, now what has to be done next is we are going to write down the slope deflection equation for each of the member at each of the joints. Okay, in general, this is what the slope deflection equation is. So Mij is equal to Mfij plus 2ei by L into 2 times theta I plus theta j minus 3 delta by L. Ij represents any two joints in the member, the near joint and the far joint. Okay, when I take up the member AB, Ij represents the joint AB. Okay, so for the joint A, I'm writing the slope deflection here, equation here. Okay, first I'll take up member AB, and at joint A, I'll write the slope deflection equation. So what it happens here, MAB is equal to MFAB plus 2EI by L. So span is 6 meter here. For member AB, it is 6 meter, and EI and I are constant, which are given to us. So 2EI by L, which is 6 meter, into 2 times theta A plus theta B minus 3 delta by 6. Okay. Now let us identify what are these values within the bracket. Theta A, you observe here, what is there at A? It is a fixed joint. No rotation will be allowed at this joint. So there cannot be any slope developing at joint A. So that's why what we have is theta A is 0. Okay. Fixed end at A. Now, what about delta? Okay, delta is the relative displacement between A and B. Okay, so here no such relative displacement between A and B is occurring. Okay, so delta will become 0 unless and until it is specified to you that there is a relative displacement in the form of settlement or sinking. This delta will remain 0 here. Okay, for this case. Okay, so delta is also 0 and theta is also 0. Theta B will exist, and we have to find out what is its value by this slope deflection equations. Okay, so finally MAB, on substituting all these values, what it comes out is MAB will be minus 90 plus EI by 3 into theta B. This is the final simplification of the first slope deflection equation, MAB. It is coming out to be minus 90 plus EI by 3 into theta B. I'll call this as the first equation of slope deflection. Okay. Similarly, what we'll do next is we'll go to joint B in member AB. Same member, we are considering joint B for writing the slope deflection equation now. Okay. That is I and J will now be B and A. Okay. So MBA, that will be equal to MFBA plus 2EI by L plus theta A plus 2 times theta B minus 3 into delta by L. Okay, this will be our slope deflection equation. And accordingly, we'll substitute for the values over here. So MFAB is 90 plus 2E and I are constant divided by L is 6 meters. Still it is member AB, so length is 6 meter. And into bracket theta A, we have identified it is 0 plus 2 times theta B. Okay, theta B exists, it is unknown. Still, we don't know what is its value. So 2 times theta B, we'll keep it as it is. And delta is 0, minus 0. Okay, so once you simplify this, MBA will come out to be 90 plus 2 EI by 3 into theta B. Okay, this is the second equation what we obtained over here. Second slope deflection equation. First for MAB, second for MBA. Okay, so we have finished with member AB, writing slope deflection equation for member AB. Okay, next we'll go ahead with what? The next member, which is member BC, this vertical column which was there here in this frame. This member BC, we'll take up this member and go ahead with writing the slope deflection over here, equations. So for member BC at joint B, it will be MBC equal to MFBC plus 2EI by L into 2 times theta B plus theta C minus 3 delta upon L. Okay, this is the slope deflection equation. And again, we'll look for the end conditions. What are the conditions at the ends of this frame? Okay, so here what I have is C is fixed. Okay, so no rotation. Theta C has to be 0. And B, it is allowed to rotate. At this joint, rotation is possible. Okay, so and also delta, the relative displacement between B and C is not there. Why it is not there is because this is a non-sway frame. Okay, so I said we'll take up a problem on this non-sway frame. Here, this A is restraining the sway. Okay, there are no chances that sway can occur in this frame. So the relative displacement between this joint B and C of this vertical member is not possible. Okay, so delta will be 0. In case sway occurs, there can be. Okay, we'll take up in that problem. But as in this problem, the relative displacement between B and C is 0. That is, delta is 0 for member BC. Okay, so for that I have substituted this delta as 0. Theta C is and C is fixed. Delta, no relative displacement between B and C. So for that purpose, these two have been taken as 0. So on substituting the other values along with this theta C and delta and simplifying, you'll get this equation, third equation of slope deflection. MBC, which is equal to minus 33.75 plus 4 EI by 3 into theta B. Okay, so this will be the third slope deflection equation. Now what we have to do is, we have one more joint in that member BC, which is joint C. So for that, the slope deflection equation is here. MCV is equal to MFCV plus 2EI by L into theta B plus 2 times theta C minus 3 delta by L. Okay, so going for the values of MFCB, theta C and delta and substituting them over here, what we have finally is MCB is equal to 33.75 plus 2EI by 3. This is our fourth slope deflection equation. So this is how we got the 4 equations of slope deflection now. Okay, considering the general form of the slope deflection equation, this equation has been used for member AB and BC, and we have written slope deflection equation at joint A, B, and C. So that will give us these 4 slope deflection equations. Okay, substitute the appropriate condition at those joints, whether rotation is possible or no, whether displacements are there, any relative displacement. So accordingly, you can substitute for them. Okay, they may be 0 or they may be non-zeros. Okay, so once you have these slope deflection equation, the next step in the procedure will be to write the condition of equilibrium. Okay, for this frame, I can write the condition of equilibrium at joint B. Okay, so what I have is, at joint B, summation of moments should come out to 0. Summation MB should be 0 at this joint. Okay, when you add up the moments at this joint, it should come out to 0. So what are the moments that are coming at this joint B? We have this MBA. Okay, this is moment MBA in the form of an equation over here, and what I have is this MBC, okay, which is also in the form of equation in terms of theta B. So both equations are in terms of theta B unknown, and we have one condition over here, so we are able to solve that. So MBA plus MBC should come out to 0. Okay, and using these two equations, equation 2 and 3, okay, MBA from equation 2 and MBC from equation 3, on substituting them, and once you simplify this, this is what the value of theta B you are going to get. So theta B is coming out to be minus 28.125 over EI. Okay, what it is indicating, this is in terms of radians, values in terms of radians, 28.125 over EI radians. Okay, minus, it indicates rotation is taking place in anti-clockwise direction at this joint B. Okay, so these two members which are connected at joint B, BA and BC, are being rotated in an anti-clockwise direction by an amount equal to minus 28.125 over EI. Okay, so this is the magnitude of rotation. Direction of rotation is anti-clockwise due to this sign, negative sign. Okay, now how it will help us further? I can obtain the bending moments at these joints. What are the bending moments that has developed at joint A, B, and C? So this value of theta B will be used in equation 1 to 4, and then we'll be able to get the values of bending moments. Okay, so when I take the first equation MEV and substitute for theta B in that, the bending moment at joint A is coming out to be minus 99.375. Okay, this is minus 99.375. So this is in anti-clockwise direction. It is coming out to be negative, it will be in anti-clockwise direction. Okay, that should be noted there. Now same theta b I have substituted in the second equation MBA. Okay, so once I calculate after substituting for theta b, MBA, the value is coming out to be 71.25 kilonewton meter. So it is clockwise movement and the magnitude is 71.25 kilonewton meter. Okay, so further MBC at joint B, okay, in member BC, the movement is minus 71.25 kilonewton meter. Okay, so it is anti-clockwise, magnitude 71.25. So I can observe these two are same in magnitude but opposite in direction, MBA and BC. So that itself is satisfying the condition of equilibrium. Okay, so that is one thing. Then finally at joint C, what I have on substituting theta b in MCB, I'm getting moment at C as 15 kilonewton meter, clockwise 15 kilonewton meter. Okay, so with this four values of moments, I can now draw the Benevolent diagram, which is actually required for me. Okay, so this is the Benevolent diagram. What is done? Ordinates. These values are plotted as ordinates, like you do for the beam. For this member AB, it is not a problem. Just plot them as ordinate 99.375. This is one ordinate 99.375. At B, the ordinate is 71.25, 71.25. Okay, so connect them by a straight line. Okay, this is my bending moment at the supports or at the joint. Okay, over this, what has to be overlapped is free bending moment diagram. If at all, if this member is treated as a simply supported beam, then what is the value of bending moment? W square by 8, 30 into 6 square by 8. It is 135 kilonewton meter. This entire ordinate at the center, it is 135 kilonewton meter. So this is the variation of bending moment for member AB. Okay, negative sign indicates it is experiencing hogging. It is bending upwards. Curvature is upwards. Positive sign indicating curvature is downwards, sagging. Okay, so at A and B, bending moment what is experienced by the member AB is hogging, and in between, at the middle portion of the member AB, the bending moment is sagging. Okay, that tells us how the bending nature is for the member AB. Okay, so that is for horizontal member. Now coming to the vertical member, this column BC. Okay, this you are done it for beams also in the same way. Now taking this column BC, what I'll do is at B, I'll take this moment. What is the direction of movement? Anti-clockwise. So when you apply a anti-clockwise movement over here, okay, anti-clockwise movement when it is applied at this joint, okay, so it will be anti-clockwise in this direction. Okay, so it is trying to bend this member BC outwards, something like this. Okay, outwards or towards right. So that's why this ordinate I have taken it outwards or towards right. Okay, that is how I have represented the ordinate for this vertical member. Call this moment at joint B in member BC over here. It is minus 71.25, minus 71.25. I'm interested in this sign mainly, anti-clockwise. So I have applied an anti-clockwise movement over here. Because of that, it is trying to bend this member, vertical member, outwards or towards right in this direction. Okay, in the same direction, I've taken the ordinate for the bending moment. Okay, to draw the bending moment diagram, 71.25 outward. I've drawn it outward. Okay, now consider this CB at joint C in member BC. Okay, what is the direction? It is clockwise. Plus 15 kilonewton meter is the moment clockwise. Okay, so clockwise. So what I have, this is the clockwise moment. What I have here, right? This is clockwise. Okay, so what it is doing, trying to do now? Again, here also it is trying to bend it towards right. Curvature is towards right. Okay, this is how the bending of this member at joint C is taking place. For that purpose also, I've taken the ordinate outwards, 15 kilonewton meter, ordinate is taken outwards. So that is how I'll identify the ordinate direction for the vertical members, okay, whether it is bent towards left or right. in the same direction, I'll take my ordinate. Okay, anti-clockwise, it is coming and hitting this member, it is bending it outwards. Clockwise, it is coming and hitting this member, it is bending it outwards. Okay, so on that basis, I've decided these ordinates, in which direction I'll take the ordinates. Okay, so that is clear how this ordinate came in picture over here in for this member BC. Okay, so these are joint movements 71.25 and 15. Over this, again, free bending moment diagram is overlapped. What is a free bending moment diagram? WL by 8. Considering that to be a simply supported beam, WL by 8, that is, it was 90 kilonewton force applied over here at the middle of this beam, in this column. Okay, so that 90 into 3 meters divided by 8. It is, it will come out, the value, I think it is not appearing, 67.5. This is the value of free bending diagram, this ordinate, 67.5. Okay, so 90 kilonewton applied at the center, 3 meters is the span. From that, this value of free bending diagram is calculated. Okay, but important is, how do you take the ordinate for these vertical members? Okay, take the direction of the movement, apply it over here, see how that member is bent about this joint. Okay, so this was here at B in member BC, movement at joint B was anti-clockwise. So when I apply anti-clockwise movement over here, it will be bending towards right. So this is taken towards right. At C in member BC, when I apply movement of clockwise movement, it will be bending towards, again, towards right. Okay, so the ordinate is also taken towards right. And then connect these two ordinates by a straight line. Over that, overlap a free bending moment diagram. Okay, so this represents our BMD, bending moment diagram, after analysis has been completed. So this was a simple frame, non-sway frame. Okay, we went for determining the degree of static indeterminacy. Okay, it is required to calculate. It is better you calculate and mention the degree of static indeterminacy. Then the fixed strain moments for each of the members and joints. After that, the slope deflection equations. Okay, and condition of equilibrium is applied at one of the joint B. That helped us to obtain what is the rotation at B. Using the value of this rotation at B, we arrived at moments. What are the moments at the joints? And taking the joint moments and the free bending moment diagram, we are able to draw the net bending moment diagram for this entire frame. Okay. Now that is the bending moment diagram. If you have to ask anything has to be repeated. Yes. I'll just take a pause over here. If you have any difficulties or doubts in this part, you can just ask them. Procedure remains same, what you have done for beam. Okay, as far as it is a non-sway frame, you will not find it difficult, but it takes a lot of time to solve these problems. Okay, you have to practice. Done. Now one more thing what is asked here is to draw the deflected shape. Okay, so these are the deflected shape for this frame. I've taken this Benevolent diagram, what we have drawn here earlier. This Benevolent diagram has been taken over here. Okay, and this will help us in drawing the deflected frame. Okay, so what we need to identify is what are these points of zero moment, point of contraflexure. Okay, so here this is a point of contraflexure, this is a point of contraflexure, this is another point of contraflexure, and one more over here. Okay, so they will tell where the bending nature is changing. Okay, so here you have hogging moment in this portion up to point of contraflexure. It should be bent upwards. You can see there's a upward curvature what is coming over here. Okay, Then after that, downwards, curvature is downwards, sagging, hogging in this portion up to point of contraflexure. At point of contraflexure, it will not experience any bending. Beyond that, what is happening here, the movement is sagging. So this is bending downwards, sagging. Then again, when you come towards B in member EB, it is hogging, bent upwards, hogging. Okay. So in member BC, similarly, what I have here, it is bent towards right, curvature towards right. Okay. In this portion, it is opposite, curvature towards left. And again, towards C, curvature has to be towards right. So that is the way in which you draw the deflected shape. You don't have to share this. For your understanding, I have shown over here. You just have to draw this diagram, only and only this diagram for deflected shape. We already have drawn the benevolent diagram here. So what is required is this, only this diagram. Okay. This is done to relate the deflected shape with the benevolent diagram so that you will understand it clearly. For that purpose, I have done this. You don't have to draw it this for your problems. Okay. Okay. And this is what is required from you. This discontinuous line is the original position of the members, whereas this continuous red line is showing the deflected shape. This is the way in which the frame gets deflected. Okay. So benevolent diagram and deflected shape, two diagrams you need to draw over here. Is that clear? Analysis of frames. What new thing you came across is there's a sway and non-sway frames. Okay, if you have not heard of that, that is the one thing. Accordingly, sway analysis and non-sway analysis will come in. Okay, this is for non-sway, and you need to plot the benevolent diagram and the deflected shape. If you have any doubts, you can just unmute and ask. Or this will be the problem for today's class. Tomorrow we'll take up next problem. If you don't have any doubts with this. Was the audio clear or no? Anybody is experiencing problem with screen sharing, viewing, or audio? Okay, so we'll end over here. If you don't have any doubts, any problem in this, we'll come and meet in the next class. Okay, thank you.